Howdy. In this video, we're going to take up the Schrödinger equation as we begin to look at the machinery or the nuts and bolts of doing quantum mechanics. The Schrödinger equation is really the underpinnings of all of quantum mechanics, and so it's a central notion for the chapter and for module number 2. What I want to start out with is just something that's a bit more familiar than most of what's going to be in today's class. And that's just the figure that's on the screen now is just pictures of orbitals, what you've been shown in Gen Chem books and elsewhere that you recognize as depicting the shapes of various types of orbitals, right? So on the top, we've got a spherical shape, which you'll recognize as being an s orbital. On the second row, we've got a set of 3 perpendicular sort of dumbbell-like shapes that describe p orbitals. And then on the bottom row, we've got a set of 5 d orbitals with their characteristic shapes, okay? You've seen pictures like this before back into general chemistry and maybe even into a high school chemistry class. But what we're going to start looking at now is the way in which we go about generating these descriptions, okay? So when we see these pictures of orbitals or representations of orbitals, what they really are is they're obtained by first finding what is known as the wave function for an electron in that orbital, and then graphing those in an appropriate way. And so today, we're going to begin to look at how we would go about doing that. So the central tenet of quantum mechanics, in some sense, is if we describe a particle, say an electron, in quantum mechanical terms, we use what is known as a wave function to depict it, okay? That wave function carries with it all of the information that is knowable about that electron. Essentially, anything that we could possibly measure about the electron, the wave function should have information related to that quantity embedded in it. So where does this idea come from? We talked before about the fact that electron diffraction was observed, which is a vivid illustration that electrons have wave-like properties, right? And so that we might need, under certain circumstances, to treat very small particles like electrons as waves, okay? When we do this in quantum mechanics, what we do is we describe our particle using what is known as a wave function. I'm sorry, I didn't have the pen selected there. We use what is known as a wave function, right? At least in principle, that wave function can be a function of both position and time. Okay, so t there is time. This is, say, a one-dimensional situation, so position is represented just by an x-coordinate. The symbol for the wave function itself there, that's an uppercase Greek letter psi, and that is what we generally use to depict wave functions. That wave function can generally be separated into 2 pieces, a position-dependent piece and a time-dependent piece. And when we do that, we get a time-dependent piece written here as c of t, and we get this piece, which is the position part, written here as a lowercase psi of x. Okay, so still for a one-dimensional problem. All right. The wave function, again, carries with it all of the knowable information. That says anything that we can possibly hope to be able to measure about the electron is somehow contained within that wave function, right? That's the basic premise of using this wave description for electrons. The wave function can include complex terms, right? And so complex numbers is one of those things you learn about in math classes and you don't actually bump into all that often in other settings for most people, but they do raise their head a little bit here in doing some of the beginnings of quantum mechanics. Once we get a little bit into this, we'll actually find that we'll want to work with systems where our wave functions tend to be real, but along the way we will go through some that require us to do a little bit of manipulating of complex numbers. So just a quick refresher, if I take my complex number, this equation says I can divide it into a real piece and an imaginary piece, right? I in there is the square root of -1, and so the IY term is the imaginary piece of things. One way to depict complex numbers is to think of plotting them in a complex plane where we have an imaginary axis and a real axis, and we locate our complex quantity by finding a point based on its real and imaginary components, all right? If we do that, we can also do that and essentially represent those in polar coordinate form, right? When I do that, I can say my complex number can be written this way. And from there, there are a variety of relationships or identities that we can use to describe things. And so a couple of those are here. These are not really going to be central to most of what we do, with one notable exception. In what I think is the next video, we will take up a problem related to the motion of a free electron. And in working through wave functions for that, I will at one point need to use some of these trigonometric relationships to eliminate some terms. And so we will pick this up very briefly, and then we'll put it aside again. Okay, we will still have to keep in mind one aspect of the fact that the wave function can be complex, and we'll come to that shortly. A significantly simplifying aspect of the quantum mechanical systems we want to consider is that we're going to deal only with stationary states, or things that are time independent. That means we can look at only the position part of the wave function. So our wave functions will generally be depicted as written here, as this lowercase psi of x, or of x, y, and z if we go to a three-dimensional problem and are still working in Cartesian coordinates. Okay, so for whatever dimensionality of the problem, we'll have that many coordinates in our situation. Why the stationary states? Why is it time independent? Because if we want to describe, for example, the 1s orbital in a hydrogen atom, the properties of an electron in that orbital don't evolve over time, right? That electron has a particular energy. As long as it stays in the 1s orbital, it will stay at that energy. And so we don't need to consider time dependence for that sort of situation. So in order to get our wave functions, we need to look at what is known as the Schrödinger equation. It's named after Erwin Schrödinger, who first postulated that this might work back again in the early 20th century. Okay, and so to get a wave function for a time-independent situation, we will have to solve the time-independent Schrödinger equation. Okay, that equation is written out here for the first time. And if we see this, we have a couple of pieces, right? Psi is our wave function. On the right-hand side, we have the wave function psi just multiplied by E, where E is an energy. Okay, so that E is going to describe what is the energy of our particle, our electron, say, if it is in the state that is described by the wave function psi. On the left-hand side, we have a piece in front which has in it the mass of the particle, and it's got the second derivative of the wave function, right? I'm using here the notation similarly as the book does, where we're using partial derivative symbols, even though we're working at the moment with a one-dimensional or one-variable problem. Okay, so it's a little bit odd, but it's what the textbook does, and so I went ahead and kept things that way. In that first term there, this is the first incidence where we cross paths with this symbol here, which is generally pronounced as just h bar. Okay, h is Planck's constant. H bar, the h with that little slash through it, is h over 2 pi. Why does that get its own symbol? Essentially because it happens very often. Okay, it happens frequently enough that having a symbol just for that is worth the going through and making that definition. And so we'll see that quite a lot as we go through the course, but this is our first contact with it. So we have the second derivative of the wave function there multiplied by some constants. Then we have function v of x times the wave function, right? When we do those things, we're supposed to get back the wave function itself multiplied by an energy E. So if I find a function psi of x that satisfies this equation, then I could say, I know that's a possible state of my system, and I know E, so I know the energy that corresponds to that state. The version written out right there is for a one-dimensional problem. We could also add x, add y, and z terms. It would get gradually more complicated if we did that. V of x in there actually corresponds to whatever would be the position-dependent potential energy for our electron, right? So if our electron were in some sort of electric field, then the potential energy would depend on where it was with respect to the poles of that field, and there'd be a functional form for that, right? So V of x would have some expressed form. We'll talk in a little bit about the fact that the first term, the one with the second derivative in there, that one actually corresponds to the kinetic energy of the electron, and the second piece, the V of x piece, corresponds to the potential energy, right? So this equation essentially says the total energy of the particle is just its kinetic energy plus its potential energy, all right? It's obviously a differential equation because it's got that second derivative piece in there, right? So in actually finding the appropriate wave functions involves solving that differential equation. How hard it is to solve depends a lot on the functional form of v of x. A problem or a question that often arises from students who are coming in contact with these ideas for the first time is what does this wave function actually mean? What does it mean to know the wave function, right? The most physically significant manifestation of the wave function is what's known as the probability density, all right? The probability density says if I take the wave function and square it properly, as I'll point out in a second, then what we get is the probability for finding the particle in a region of space, okay? So if I was really in a one-dimensional system where I have just an x-coordinate, take psi squared at point x, and that'll say what is the probability that the electron is at that, within a space that is as wide as that x-coordinate plus some small dx, okay? The figure to the right there is actually a hydrogen is the probability density function for a hydrogen atom, for the 1s orbital of a hydrogen atom, okay? In that plot, the density of the blue dots represents the probability of the electron being found there, right? So this says where the dots are heavy in the center, that says near the nucleus of my atom, there's a large probability of finding the electron. Okay, as I get further and further away from the nucleus, you can see the dot density drops down. That means it gets less and less likely that the electron would be as far away as, say, up here on that z-axis, okay? The tapering down of that probability is going to actually be asymptotic if we looked at the form of that function, which means, among other things, that we can't really put a firm edge or a hard boundary on an atom because the electron has some small probability of drifting far away from the nucleus on occasion, okay? But that's what it would mean to have this probability density function. Okay, it's called a density function because if it was in 3 dimensions, then it would have units of 1 over volume. In 1 dimension, it would have units of 1 over distance. Okay, it says down there on the bottom of the screen, you'll notice it's labeled as psi star psi. That is what I was referring to when I said that we have to properly square the wave function. So where this says up here that I have the absolute value bars around my psi squared. What that means is because the wave function can be complex, the correct way to square it is to take the complex conjugate, which is what this star here means, right? If I take psi star, multiply that by psi, that's what I mean by having psi squared. To get psi star, we would take the wave function itself, psi, any place where there's an I, the square root of -1 term in that expression for psi, we will replace it with minus I. So we flip the signs on all of the i's. When we do that and then multiply those two things together, we guarantee that psi squared will be real. If psi squared is going to be related to the probability, then it needs to be real, right? We can't have an imaginary probability of finding the electron at some particular point, right? And so that's kind of the explanation of why we go through that. We can generally write the Schrödinger equation as an example of one that is often written in terms of operators. Operators play an important role in quantum mechanics. Essentially, operators, we can develop an operator that corresponds to any particular physical observable. Right? Any quantity we could measure, we could put together an operator, have that operator act on the wave function, and that will get us the information about that property. In the Schrödinger equation, if we write it in operator form, the hat here, this tells me the hat on my H, which that's kind of awkward with it up there, so let me actually take that away. If I get rid of that, because it kind of covered up what the fact that I had that there in the first place. If I take that H operator, I have the operator act on the wave function psi, and then I get back psi itself times the energy, right? Our Hamiltonian operator written out for the one-dimensional case looks like what's down here. In this formulation, this first term, that's the kinetic energy, and this piece is the potential energy. Right. I put those together and I get the total energy for my electron, for my particle, okay? Notice that the wave function itself, I take the wave function, I act on it with the Hamiltonian, and then I get back the original wave function times the energy. right? The energy, the E in E psi on the right-hand side is just a constant or a collection of constants, right? It's not an operator, doesn't have the hat on it in the symbolism. And so some of you may remember from math courses that that means this equation is an eigenvalue equation, okay? In here, the operator is H, that's the Hamiltonian, E is the energy, and that energy is an eigenvalue, meaning it just is a constant multiplied by the original function. A wave function that satisfies that equation, we say it's an eigenfunction of H. All right. In this case, because we know the H operator includes a second derivative piece, right? And so that means we can sort of guess based on that the kinds of terms that are going to show up in our wave functions that satisfy the Schrödinger equation. Think of functions you know that you can take the derivative twice and get back to the same form as the original function. Those include sines and cosines and exponentials, right? And sure enough, those are the kinds of terms that we're going to see all the time in wave functions, because they're the things that are going to give back the original functional form when we act on it with the Hamiltonian. A simple example of an eigenvalue eigenfunction pair down on the bottom there. Suppose I have an operator that is just the first derivative, right? Just d dx. If I take that first derivative operator and let it act on e to the 2x, when I do that, it's fairly easy to see that my result is 2e to the 2x. So that says that my function e to the 2x is an eigenfunction of the derivative operator, and the eigenvalue is 2. When I say the eigenvalue is just not something that's multiplying the function, the important thing is that eigenvalue cannot have any of the variables in it. So in this case, my eigenvalue cannot have any x terms in it. Okay, if it did, if I put in e to the 2x squared in my exponent, for example, then it would not be an eigenfunction of that derivative operator, because then there'd be an x in the piece that was out in front of my my exponential. Right? And that would mean it was not just multiplied by a constant. So once we know that we're dealing with these things, we want to talk a little bit about the idea of what is sometimes known as the correspondence principle, which says that any observable property, anything I could measure, the energy of the electron, the momentum of the electron, we could do this with angular momentum or other quantities, anything like that, there is some operator we can put together which will depict that quantum mechanically, okay? If I do that, the eigenvalues, in the case that my function is an eigenfunction of that operator, the eigenvalue we get is just what would be the value of that property, right? So the energies, the wave functions are eigenfunctions of the Hamiltonian, and that means the energy comes out of that, and that is the energy we would expect. So if I put in the wave function for the 1s orbital in hydrogen into the appropriate three-dimensional Schrödinger equation, when I do that, I could get, this is the energy of an electron in that orbital, okay? And that's a powerful thing. That says we can predict what the energies should be, okay? Little bit of a limitation on that. It turns out that you can only really analytically solve the Schrödinger equation for atoms that have only one electron, right? So you can do a hydrogen atom and get an exact solution. You can do helium plus, but not neutral helium. And the reason for that is as you get more electrons, there are more terms in the potential energy, because the electrons will both be attracted to the nucleus, but they'll also repel each other, right? That doesn't mean we know nothing about other atoms. There's plenty of really good numerical approximations. It just means that you have to be computationally clever to be able to get results for things. But we will focus mainly on things that are not more complicated than the hydrogen atom, places where we can get exact solutions to the Schrödinger equation. So let's look at some of these operators. The ones that are already packed into the Hamiltonian, we have the kinetic energy operator and we have the potential energy, right? The potential energy we sort of just write this way most of the time, because the details of that potential energy would depend on what kind of problem are we talking about, right? If I was talking about a hydrogen atom, then the potential energy would depend on the distance of the electron away from the nucleus, right? Because I have a positively charged nucleus, negatively charged electron. The potential energy of that electron depends only on how far apart they are, right? If I had a particle moving in an electric field, then I'd have a potential energy that somehow depended on where it was along the possible range of x values. right? So the operator for kinetic energy just is the one that is the first term in the Schrödinger equation, which has the mass of the particle in it, and it's got this second derivative piece, okay? The potential energy, again, we'd have to put together the form of that V of x depending on what the actual situation or problem we were looking at was. So let's take a first shot at doing something with one of these. This is our kinetic energy operator up here. This is a simple wave function down there, e to the ikx, right? That we'll look at that next time, I think, as a wave function that could describe the motion of an electron that's just free to wander around in space. If I take that wave function and that kinetic energy operator, I should be able to find what is the kinetic energy that corresponds to that wave function. So let's try that. So here's my operator again and my wave function, right? So what I'm going to do is I'm going to say that if I do this, I should get that minus h bar squared over 2m, second derivative, I missed the x. Call it ek psi of x, and then I'm going to put in that form. Okay, so what I'm going to do is I'm going to just evaluate this side, I think. So I'm going to say, if I do this, I'm going to have minus h bar squared over 2m. And now I need the second derivative of e to the ikx. When I do that, I'm just going to go ahead and figure out what I'm going to get. If I take the first derivative, I'm just going to get ik e to the ikx. So this thing is equal to, I'm just going to keep the minus h bar squared over 2m out here, right? And then I'm going to have, I'm really bad at this. I'm sorry. I have the derivative. I have to take the derivative again after I've taken one derivative. When I take one derivative, what I get is ik e to the ikx. All right. And if I do that one, then that says I'm going to get I squared k squared e to the ikx, which is equal to minus k squared e to the ikx, right? And out of all of that, if I take this form now, I can say that's equal to this side, right? This piece here is my psi, and that means that I would get E k, my kinetic energy. That was supposed to be a k. I swear I wrote a k. Sorry, that's a k. Pretend that's a k. My kinetic energy is just going to be, according to this, equal to minus k squared, right? Minus k squared, and I've actually got the, I lost a piece. I've still got this piece floating around out there, okay? And so I need to multiply my minus k squared piece by that because that got lost along the way. And so my kinetic energy is actually going to be equal to minus h bar squared over 2m. That's the piece from the constants, and then I have to multiply that by minus k squared. And when I do that, I'm going to get h bar squared k squared over 2m. All right, so that is then the kinetic energy for my particle that's represented by this wave function that we started with. All right, and that's just sort of the mechanics of how we would go through and find the value for one of these things. All right, suppose we wanted to have figure out something else about our particle. We might decide that we wanted to know the momentum of the particle, say. right? And so in general, there's going to be a correspondence principle between the quantum mechanical properties or the quantum mechanical operators and the way we would find things in classical physics, all right? So if I take classical mechanics and I want to get the momentum from the kinetic energy, I have this expression over here, which says the kinetic energy should be equal to p squared over 2m, where p is the momentum. Okay, and that's just a classical physics relationship. I know that in quantum mechanics, we just said this one is our expression for the kinetic energy operator. And so if I want to find the operator for momentum, what I need to do is I need to find an operator that works so that my momentum operator, the p hat in this piece down here, if I do that twice, over 2m, I have to get my kinetic energy operator, right? Because p squared over 2m has to be the kinetic energy. And so that's how we would go about finding our momentum operator. If I do this, those are the things that I know, right? And so I want to take my operator and look at how this actually plays out. In order to do this, I want to say that looking at this piece, I have the 2m down here, right? So what I need is if I lose the 2m from this, I will have left minus h bar squared. Someday I will learn to stop doing that, maybe. D squared dx squared. Right, that should be equal to my momentum operator squared. Right, because that says I've done the momentum operator twice to get to there, right? If I take that, I'm going to need one. I'm going to need an h bar, and I'm going to need a derivative, and then I've got a minus sign in front of this, so I'm going to need an I, all right? And so one way I could write that is I could take that and I could say my momentum operator looks like it will work if I say that it's I, h bar, and a derivative. Okay. This can be written in a variety of ways. Your textbook, our textbook likes to use this one, which says that the momentum operator is equal to h bar over I and the derivative. Okay, those don't actually meaningfully differ from one another, right? Because the I is going to end up coming into play essentially when we have the wave function squared. So we're getting to real quantities. The momentum has to be a real quantity after all, right? And so those are going to work out one way or the other. For that, there's actually another argument that could be made, which says that if we put a minus sign in front of there, some things work out a little bit better. But this is the form that your textbook likes for this. And the reason why there are multiple forms that work is just because of some of the quirks of the imaginary numbers in the first place, right? But we will use this form because that's the one that your textbook uses for the momentum operator, okay? All right, so that gives us the basics of operators, right? We could, as I mentioned, there are other operators we could put together. We will latch onto some as needed as we go through the course in specific instances, but the operator is a way that we go about getting information from things, okay? So let's do one more thing with this. We have a momentum operator now. So let's find the momentum for the particle whose wave function we had before, right? So if this is my wave function, this is the wave function we put together, and we found the kinetic energy for it earlier. Let's now look at its momentum, right? My momentum operator, we just decided we're going to use P equal to h bar over I, like that. And so that means my momentum for this case is going to be, I want to take that operator, h bar over I, derivative. I want to have that act on e to the ikx. When I do that, when I take the derivative of e to the ikx, I'm going to get ik times e to the ikx, right? So I get h bar over I. Then I'm going to have this times ik e to the ikx, right? And that says that from that, I actually get my momentum, right? My i's are going to cancel. My eigenvalue there is h bar k, and that means, so I could say that this is equal to h bar k times my original wave function, right? And that means that this piece, my eigenvalue, that's the momentum. Right? So my momentum here is just equal to h bar k for my electron described by that particular wave function. Right? Once I have the operator, in this case, because the wave function is nice and simple, working through what that gives me for the momentum is straightforward. Right? That's an example of another one of how we would use the operator to extract the information from the wave function. Right? So when I say the wave function carries all the information or contains all the information, we've shown here fairly briefly how we get the kinetic energy and the momentum of the particle that would be described by that e to the ikx wave function. Right? So that's the first two examples of things we could get from that. Again, there are other operators that would get other quantities, and we'll look at some of those going forward. Thanks.